All right, so we're in section 3.6 now, where we're going to be dealing with the derivatives of logarithmic and inverse trigonometric functions. And the approach that we're going to be taking for both of these is to first look at a general formula for determining the derivative of an inverse of a function, assuming we know the derivative of that original function in the first place. Your book doesn't take this approach, but it does as one of the exercises in the back. I want to say it's exercise 82 or something like that. It does mention this little formula that we're going to derive at the beginning and asks you to derive it there. I didn't assign that problem. We're going to take a different approach than the book takes and start with deriving this formula and then use that to get the differentiation techniques that we're actually looking for in this section. So before we do that, I wanted to run through a quick review of what inverse functions are. So you talk about this in intermediate algebra, and then it comes up again in trigonometry, where you learn about the inverse trig functions. College algebra, you'll talk about it. Usually it's introduced, though, right around the time that you start talking about logarithms, because a logarithm is an inverse of an exponential function. The idea of an inverse function is it's a function that undoes what one function does in a certain sense, and we'll make more sense of that in a moment. That's obviously a terrible definition, so we need something a little bit more precise. So a function f of x, if it has an inverse, we use this notation. It looks like f to the power of -1, but it's not actually an exponent. This does not represent the -1 power. It's just we're using the same superscript notation as you would for exponents to mean something else. So this is another function that's related to f of x by these two properties. F of f inverse of x is equal to x, and f inverse of f of x is equal to x, for all x for which either of these would be defined. So what that means is this f and this f inverse, in a sense, cancel each other out when you do function composition with them, leaving you with just the input x. And same if you do it in the other direction, f inverse of f of x. You can think of this as the f inverse and the f canceling each other out when you do function composition, leaving you with the x on the inside. Okay, so one of the first inverse functions you look at is the natural logarithm, or really just any logarithm, because the natural logarithm is the inverse of the exponential function e to the x. If we define f of x to be e to the x, then its inverse, f inverse of x, would be natural log of x, because this property is satisfied. So f of f inverse of x in this case would look like this: e to the power of the natural log of x. We know from algebra that the e and the natural log cancel each other when you compose them this way, leaving you with just that x right there. Done the other direction, f inverse of f of x would look like this: e to the natural log of e to the x. The natural log and the e cancel each other in this case as well, leaving me with just the x. Okay, so this is one example of an inverse function, but there's plenty more. Now, one thing you also learn about when you first talk about inverse functions is this concept of a function being one-to-one. What does it mean for a function to be one-to-one? Well, the technical definition is this. The function f is one-to-one if f of x1 equals f of x2 implies that x1 equals x2 for every x1 and x2 in the domain of f. So this definition, if you're not used to working with definitions like this, might not seem very intuitive. You may not know what it's saying here. So to clarify, if I say f of x1 equals f of x2, what that means is if I plug x1 and x2 into this function, then they each produce the same output. Okay? A function that's one-to-one can never have two different inputs giving you the same output. That's what would cause a function to not be one-to-one. So what this is saying is that if you have x1 and x2 and plugging them both into f of x gives you the same output, then they must have been the same input to begin with. In other words, there's no difference between these numbers. We have a way of determining if a function is one-to-one or not if we have a graph of that function to look at, and we use what's called the horizontal line test. So for example, if f of x is equal to e to the x, then the function gives me a graph that looks like this, and anywhere I put a horizontal line through that graph will only ever hit the curve at most one time, so it's never going to hit the curve 2 or more times. That means the exponential function passes the horizontal line test, which means that it's 1 to 1, which guarantees the existence of an inverse function. That's how we know that the natural logarithm exists and is a function. Now, the reason the horizontal line test, the reason we need a function to be 1 to 1 is because of what the relationship between the graphs of a function and its inverse is. So if a function has an inverse, like the exponential function here, then its inverse's graph will look like a reflection of the exponential function across the line y equals x. So here we have the graph in blue of the natural log, and it's a perfect reflection across this line y equals x of the exponential function. And this is the case for all functions that have inverses. If a function has its inverse, or has an inverse, then the graph of its inverse will look like a reflection across the line y equals x. The reason for this is because what an inverse essentially does is it swaps the inputs and outputs of a function. So any point on this function, if I look at its x and y coordinates, then the corresponding point, which has the same y coordinate as the x coordinate here, and the same x coordinate as y coordinate here, that should be a point that shows up on the inverse's graph. So again, if I take all of the points on my function y equals e to the x, or whatever function I have here, and swap their x and y values, the points that I would get as a result would be all of the points on this graph. And that's what reflecting across the line y equals x essentially does. The reason the horizontal line test is important here is because every horizontal line that I put through this red curve, once reflected across the line y equals x, will become vertical lines through that inverse function. So if a horizontal line passes through this curve at more than one point, then that would correspond to a vertical line passing through this inverse function in more than one point, meaning that that thing wouldn't actually be a function in the first place. So having the 1-to-1 property guarantees that when we take the inverse, the result is a function. Okay, this is all review. We haven't gotten into any calculus yet, and we have a little bit more to do before we can start talking about derivatives. So here's an example of a function that is not 1-to-1. It's f of x equals x squared. This function fails the horizontal line test in multiple places, right? I could put a horizontal line right here, and I would be hitting this curve twice. So the function by itself should not have an inverse. And you can verify that because if you reflected this across the line y equals x, I would get a right opening parabola, which would fail the vertical line test. It wouldn't be a function. However, it is often the case that we are given a function which is not 1-to-1, but we would still like to come up with an inverse for that function, or at least some kind of an inverse. And this can be done by taking the function that's not 1-to-1 and restricting it to an interval on which it is 1-to-1. So for example, this function right here, f of x equals x squared, even though it's defined for all real numbers, I can artificially restrict its domain to just the non-negative real numbers. Essentially what that does is it cuts off the left branch of this parabola, giving me something that looks like this. So by cutting the graph in half, the right branch of that parabola produces a curve that is 1-to-1 because, the function would be 1-to-1 because the graph passes the horizontal line test now, whereas it didn't before. After making that restriction, we can find the inverse of that function, which turns out to be the square root function. And that's what we would have expected. The x squared function should be the inverse of the square root of x function and vice versa. You can also see that the graphs of x squared and the square root of x are still reflections across that line y equals x as we expected. Okay? Now, we want to get into a method for finding the derivative of the inverse of some general function that has an inverse. So let's suppose we have a function f of x, and I'm going to say y equals f of x, and let's suppose also that this function has an inverse, f inverse, which this, again, that's what this notation denotes. If I were to take f inverse of both sides of this, then on my left side I would end up with f inverse of y. On my right side I'd end up with f inverse of f of x, which by definition, as we said at the beginning of this section, is equal to x. Okay, so to say that y equals f of x is the same thing as saying f inverse of y equals x. Now what I want to do is use implicit differentiation on to try and find a derivative for this inverse function. So I'm going to do d dx of both sides, thinking of y once again as a function of x like we have here. Okay, so the derivative of my left-hand side is a composite of two functions of x. I have f inverse as my outside function and y as my inside function. So the derivative would look like the derivative of the outside function, which we don't know what that looks like. Remember, the goal is to find that. F inverse, I put that in parentheses and put the prime notation to denote that we have the derivative of f inverse. The inside function stays the same. Remember, this is like the chain rule, but then we multiply by the derivative of the inside function, y prime. On my right-hand side, I have d dx of x, which is just 1. Okay? Now I could divide both sides by y prime, which would give me f inverse of y. Remember, this is the thing I'm trying to find here, the derivative of my inverse function. It's equal to 1 over y prime, or because y is equal to f of x, this is the same thing as 1 over f prime of x. But x, as we set up here, is the same thing as f inverse of y. So another way of writing this is f prime of f inverse of y. Now you might be looking at this last step and thinking, well, I already had something that looked pretty nice right here. Why did I want to do this? And the reason is because if here I'm thinking of my input as y, I want the input over here to match that. Okay, because f inverse is a function of y, so the formula for the derivative of that thing should also be a function of y. Now typically we're not going to use y's in practice, we would be using x's, and at this point the y is really just a label for the variable being used here. So if I were to change both of these y's into x's, nothing really changes, and I can state my little formula this way. F inverse prime of x is equal to 1 over f prime of f inverse of x. Okay. Now you're not going to be using this formula much for, actually you're probably not really going to use this for anything in the homework, but I'm going to use this to derive the differentiation techniques for a few functions that happen to be inverses, and those techniques are the things you're going to be using. One thing, I want to point out a couple of things here. We launched into this making some assumptions. Kind of the biggest assumption is that a derivative exists in the first place. Going from here to here, I'm actually making the assumption that f inverse has a derivative at all. Okay, we know, or we're implicitly assuming that f of x is differentiable, and it turns out that would imply that the inverse is also differentiable with one little exception, which I'll mention. So take a look at these two functions, y equals x squared and y equals the square root of x. The x squared function was the original function we were working with. And we know that function is differentiable, but even if you didn't know that right away, remember we talked about how to look at the graph of a function and use that to determine if the function is differentiable at particular points or not. We said that differentiability implies a certain smoothness. So notice the x squared function is not discontinuous anywhere. It also doesn't have any corners or cusps anywhere, and it also doesn't have any vertical tangents anywhere. Those are the places to look on a graph to see if we don't have differentiability. Now, because the inverse is just the reflection of this curve across the line y equals x, reflecting this curve is not going to make discontinuities suddenly appear. It's also not going to make any corners or cusps suddenly appear, because those would, if there was a corner in this graph, then it would correspond to a corner in this graph, of which there are none. The only place where there's a possible issue is if this function my f of x or my y equals x squared function has a horizontal tangent anywhere. So notice the original parabola, which is on the previous page, I'm not going to go back to it, there would be a horizontal tangent at 0, right? Because that's where y prime would be equal to 0. Once I reflect this curve across the line y equals x, that horizontal tangent is going to become a vertical tangent. And remember, vertical tangents are places where your derivative is undefined. So the only real place where we could lose differentiability after finding the inverse of a function is anywhere where the original function had a horizontal tangent. That's actually accounted for in this formula, because if the original function has a place where f prime is equal to 0, notice down here we're taking f prime of something. If this is equal to 0, then we're dividing by 0, and that's where that undefined part comes from. Okay? So far it's been a lot of kind of theory and stuff like that dealing with this formula, but I want to start applying it now. I want to start using it. So the first thing we're going to do is test this formula to see if it's working correctly. We're going to work with the function f of x equals x squared once again, and to ensure that it has an inverse, we're restricting it to this interval 0 to infinity. And we know from what we just talked about that the inverse of this function should be the square root of x. So what I want to do is find the derivative of the square root of x in two different ways. I want to use this formula that we just came up with, and then I also want to just use the power rule because we've already taken the derivative of this. I just want to make sure that I'm getting the same result regardless of my approach. So what do we need in order to use this formula? Well, f inverse of x is equal to the square root of x, and I'm looking to take the square root of, or the derivative of this function. So I'm looking to find this. Looking to my formula here, what I need is the function f inverse of x, which we are given, and then I need f prime. Now remember, this is not f, this is f inverse. So the f prime that it's referring to is the derivative of this function. So in other words, in order to find the derivative of an inverse, I first need to know the derivative of the original function. But that's easy. We know that the derivative of x squared is 2x. So using this result, the derivative of my square root function, or the derivative of f inverse of x, the way that we've labeled it here, is equal to 1 over f prime of f inverse of x, f prime being 2x, and f inverse being the square root of x. I'm plugging the square root of x into this, which gives me 1 over 2 root x. But you can confirm really easily, and we've done this already, that if I found the derivative of the square root function using the power rule, this is exactly what I would have gotten anyways. Okay? So that's confirming that our formula that we just derived is doing what it's supposed to. It's giving us a correct answer for a derivative. But this particular example has given us no new information because we already knew the derivative of the square root function. We wanted to use this formula to find derivatives of functions we haven't dealt with yet. So what we're going to do is find the derivative of a general logarithm, log base b of x. And I want to be thinking of that logarithm as an inverse. So that means if I'm looking for something to call f of x, I would want it to be an exponential function. Let's let f of x equal b to the power of x. This would mean that the inverse function that I'm looking at is log base b of x. Okay, now we've already found the derivative of this general exponential function in a previous section. We found that it was equal to b to the x times the natural log of b. Okay, and this is something that we'll need in our formula. So the goal now is to find the derivative of log base b, or the derivative of f inverse, which is this. Here's the formula. We need to take f inverse of x, which is this, log base b, plug it into f prime, which is this, b to the x natural log of x. So that looks like this, b to the power of log base b of x times the natural log of b. But this expression right here, b to the power of log base b of x, those are inverse functions of each other. So we can cancel the b with the logarithm and just leave the x. 1 over x times the natural log of b. And this is how we take derivatives of logarithms. d dx of log base b of x is equal to 1 over x times the natural log of b. Remember, the natural log of b is a constant. Okay, so this works for any logarithm, but the most interesting and honestly the most useful case is the natural log, because the natural log is the same thing as log base e of x. And so if I'm looking for the derivative of the natural log function, I'd be plugging the number e in for my b here, 1 over x times the natural log of e. Of course, the natural log of e is equal to 1, so this is really just 1 over x in that particular case. And that's the simplest version that we're going to get out of this thing right here. The derivative of my natural log function is just 1 over x. Okay, let's do a couple of examples here. I'd like to find the derivative of the log base 3 of x. Okay, this is just a direct application of this formula. So that would equal 1 over x times the natural log of b, which in this case is 3, ln of 3. Okay, pretty much nothing to do there, right? It's just a direct application of that technique. So we want to look at more interesting cases. Let's do one involving a natural log. Y equals the natural log of x squared plus 6x minus 1. So here I would need my chain rule because I have a function sitting inside of another function. The outside function in this case is the natural log. So what is y prime? Y prime is going to equal the derivative of the outside function, but evaluated at the inside function. So the outside function, my natural log, takes the reciprocal of its input. ln of x becomes 1 over x. In this case, the input is that function. So I get 1 over x squared plus 6x minus 1. Then because this is the chain rule, I need to multiply by the derivative of that inside function, which would be 2x plus 6. Of course, I would prefer to write that this way. And I'm not going to simplify anything, okay? Now I want to point something out about this example. The end result was a quotient, and the denominator in that quotient was the argument in my natural log, and the numerator was the derivative of that argument. And there was nothing special about the quadratic polynomial that was in there. It's better to recognize a more general pattern here. So the pattern is this. If I want to take the derivative of the natural log of some function of x, like that, in this case the function of x was x squared plus 6x minus 1, I'm always going to get the same thing, f prime of x over f of x. I'm going to get the derivative of the inside over the inside. That's what this is saying, okay? So you can use this to more quickly work through problems of this type. Let's go ahead and end this video here. We got more examples to do in the next.